Okay, hello everyone, welcome. We are live for today's talk of CEDIM from the Industrial Design Department. Today we are going to talk about the topic of bio-trajectories in computational design. The talk will last 1 hour, and the last 20 minutes will be left for questions and answers. So please write your questions through the Q&A section on the bottom of your screen. And we are in company of Boyan Mihaylov. Boyan is a computational designer at Joris Larman. He is a designer with background in architecture and engineering. His design approach focuses on the development of computational tools for exploration, analysis, and fabrication of complex geometries. Throughout his professional and academic experience in Germany, Bulgaria, and the Netherlands, he has worked on many built design projects, adopting from an early point of his career a methodology that aims to decompose design tasks into mathematical logics. Welcome, Boyan.
Thank you very much, Georgia. Thanks for the invitation, and thanks to CEDIM for this nice opportunity to present to you. Well, basically, this is a peculiar topic because in this situation we're in now, many of you probably just like me have used this past year, the time in this last year, to take a breath and take a look back and sort of reevaluate certain things in the things that you're doing. And so did I. And this is why I want to take this opportunity of this lecture, not so much to show my own work, but rather to present a more general personal reflection on the field that I'm working in, namely the field of computational design. And some of this stuff might be obvious to some. Hopefully, it would shed more light onto the topic for people who are just getting to know computational design, and hopefully it would send some waves among the very community of computational designers, inspiring new futures for its evolution. First, a bit of introduction on my own background, so that you know from what position I'm approaching the whole problematic. Currently, I'm working at Joris Larman Studio, a design studio based in Amsterdam, where we use the newest design and fabrication tools of our current technological shift to design some unique objects anywhere in the scale range from furniture to large sculptural screens to this 10-meter long footbridge that is 3D printed out of stainless steel, that you can see on one of the photos. My journey into the field of computational design started about 10 years ago when I was at the University of Stuttgart. At about that time, the Institute for Computational Design, led by Professor Achim Menges, was just beginning to sort of establish itself as an important player in the German design academia. So when I witnessed the first pavilion, the first research pavilion they constructed on the university campus, I was really struck by the radically different approach they had towards design and materiality. And this complex aesthetics of what they were teaching and what they were demonstrating through this pavilion somehow subconsciously resonated with my interests and sparked my curiosity. By getting more and more involved in many of the projects of ICD and ITKE, my view of computational design was strongly marked by the design thinking that the Institute was teaching. And concepts like intelligent material systems or biomimetics became very prevalent in the prevalent notions in the way I was thinking about my design projects. In many ways, the topic of biological nature and the high technological analysis of it to create better designs was always somehow there in the process. Throughout the following years of experience gathered afterwards, during the numerous computational design projects I was involved in during my time in Germany, Bulgaria, and the Netherlands, I was trying to gradually form a deeper understanding of the design philosophy connected to computational design, which so I could communicate it to people when they asked me why exactly is it that I'm doing this, and how is it making the world a better place. And what I found out along the way is that computational design is less of a well-defined school of design, but more of a methodology which can manifest itself in many different nuances of design ideology and philosophy. So in this lecture, I would like to present some of my insights into the relationships between design and computation, as well as biology or biological nature or the living world, any way you wish to interpret this, which, as I will show, is intrinsically connected to the other two topics. And as computational design becomes ever more established and popular among designers around the world, I would like to also analyze its potentials, perhaps see if there were any promises that it has been giving, and maybe some disappointments that I've personally had with it in relation to biological nature. And I also want to hint on the other side on some positive trends towards the end of this lecture, which I hope perhaps could help regain its computational design's innovative glory and save it from potential stagnation in the future. So to start with, let's dive a little bit into what computational design actually is and in what ways it came to be. For this, I want to first refer to a paper written by David Stasiuk called Design Modeling Terminology, which very clearly differentiates some terms connected to digital design modeling, which are oftentimes mistakenly used in an interchangeable way in the public discourse, but actually represent slightly different notions, which are linked to each other in a hierarchical sense, but are also positioned on different levels of complexity. To start with, there's procedural modeling, which David Stasiuk describes as one that uses an explicit instruction set to produce a model outcome. This sort of, you can view it as an opposition to what we might call first-order modeling or hand modeling, so the purely intuitive subsequent drawing or sculpting of a design as a model. And instead, procedural modeling is, in the broadest possible meaning, constructing algorithms to create a design. On the other hand, Stasiuk defines a parametric model as a set of equations that express information regarding the deployment of an architectural information system as explicit function of a number of parameters. So here, basically, the procedure used to control the design is explicitly defined as a mathematical function, which takes certain numerical inputs and processes it into an output, pretty much like what BIM software does, like building information software. Computational modeling is a form of both procedural and parametric modeling, which, however, takes things to another level of complexity. Achim Menges and Sean Alquist, among others, try to separate the notion of computerization which indicates literally the translation of values or operations into a computing machine, pretty much like using a calculator, from the notion of computation, which produces new information from the inputs, which is was not directly known or not necessarily predictable in advance. So there's a certain novelty created by this process. Or in other words, computational design must be seen as being information producing in makeup, moving beyond translational representation through a process of transformation. So computation is the expression of a system of reckoning that informs through operations of transformation, modification, or the ordering of observed physical or symbolic entities. In this context, Stasio points to a very interesting quote from von Förster, which states that computation is any operation, not necessarily numerical, that transforms, modifies, rearranges, or orders observed physical or symbolic entities. So in this sense, if we view computation as the way to process information, couldn't we draw a parallel to the very information processing mechanisms that produce all life, all biological life as we know it, such as DNA transcription and the various enzyme mechanisms that take place on a cellular level, much like a tiny computer, tiny biological computer. Biocomputation, or this duality between biological life and computation, has been of interest to scientists for a long time and has been identified as such because information exchange mechanisms can be observed in many systems like plants, fungi, and colonies of microscopic organisms. And they have been doing this for long before the computer was invented. If you take as an example the weak electric currents that flow through the mycorrhiza networks in between the branches of trees and serve as a sort of information travel to transfer to warn other trees for potential dangers and sort of work as an internet network below the ground for trees. And as early as the pioneering days of computation, this potential of computers to, or computational processes to sort of create patterns which are very similar to phenomena observed in nature were recognized. As we know, Alan Turing was one of the first people who sort of took the creation of a computing machine from beyond from a simple calculator to something with more sophisticated, basically sort of almost opening the gates to artificial intelligence with this. And he also recognized the certain algorithms that can create patterns, self-organizing patterns, which come up in many examples in nature. And these patterns are now known as Turing patterns. Around the same time in the 1940s, Warren McCulloch and Walter Pitts took inspiration from the neuron cell, as it was known back in the days by neuroscience, and devised the first artificial neuron, paving the path to what we now know as machine learning or artificial neural networks. A little bit later on in the 1970s, the mathematician John Conway explored yet another algorithm with very simple rules, which can yield complex behavior. So he applied this algorithm to a grid of little square cells. He called them cells, and they had these binary states, whether either they were dead or alive. And through these neighbor-based rules, they could form emergent patterns which could move around, multiply in very specific ways, devour each other, kind of similar to patterns observed with living organisms, and hence the name of this algorithm, Conway's Game of Life. And such emergent patterns were sometimes directly related to biology. For instance, when the Hungarian biologist Aristid Lindenmayer developed the so-called L systems, an algorithm also with simple rules that could generate branching structures similar to those of plants. If you zoom in on those structures, you can see a self-similarity on different levels, which directed a lot of attention to the fractal nature of natural formations. This fractal structures would be later unveiled in all their glory by the mathematician Benoit Mandelbrot, who provided a stunning insight into the infinite fuzziness of that can be found in nature, in natural formations such as coastlines or gases or other mediums. And while all these exciting developments were happening on the forefront of computer science and mathematics, in the meantime, the designers also adopted the use of computers, and their computer modeling tools evolved from mere 2D drafting boards to something more complex, 3D modeling instruments where they could sort of see their designs in 3D space. That was thanks to the evolution of computer graphics, to which a big contribution was paid, surprisingly, by the entertainment industry in this time. So for the production of animated films or computer games, many computer scientists worked for studios like Pixar or maybe some gaming production companies, and these scientists developed algorithms to depict natural phenomena, which became a standard for a lot of the 3D modeling software that we have even up to date. Some examples are metaballs, Perlin noise, the Catmull-Clark subdivision, and particle systems. And whoever has worked with different 3D modeling software should have, at least at some point, come across some of these terms. So all of these algorithms had the goal to have an accurate give an accurate representation of forms, of shapes and phenomena that occur in the real world. And in this way, computational tools became an artistic instrument to recreate the world virtually, and to, in some way, gain control over its physical laws, and even to be able to create new imaginary worlds which defy the laws that we know from our real life. This, of course, was this inspired a lot of designers as well, and because it unleashed a lot of possibilities for the expression of designers at that time. It gave a new range of expression of imagination and ideas, which some architects and designers used as an opportunity to counter the so far limiting and kind of solemn and utilitarian morality of for example, the modernist school before that. And sometimes it was the architecture offices themselves who pushed the boundaries of CAD software even further through developing their own software to serve their design needs. For instance, a good example is Geary Technologies, which was founded by Frank Geary for some of his architectural projects. And you could kind of see that there was a certain fascination for this so-called organic form, which was manifested more in a top-down sculptural way. So the designers usually had a vision which they needed to find the tools to express, and in this sense, it was top-down. And obviously, these new tools allowed them to create some previously unattainable shapes, the shapes of nature. It also became evident at the same time that this vision of organic space in architecture needed some kind of redefinition of the industrial standards, which, for instance, people like Lars Spaubruck already saw in the so-called mass customization, as opposed to the so far established mass production paradigm. And while many designers were appropriating the organic shape driven by more aesthetic motives, some designers and engineers sought to harness the very morphogenetic processes behind the natural form, and to use these processes or abstractions of them to inform their designs. Such approaches were already known from Antoni Gaudi's experiments with the hanging chains for Sagrada Familia, but these approaches were also very much the focus of the German engineer Frei Otto, especially in his exploration of self-organizing material systems such as soap bubbles or weaving systems of threads and others. In general, Frei Otto was designing with the computational processes of nature instead of working against the physical forces. So this led to equally fascinating results, and it also opened the eyes of many designers and engineers to what a huge potential it can have to look at the intelligence of nature and let it inform your design, integrate it in your design. Biological organisms, specifically as a natural system, being a complex and self-organizing manifestation of nature, proved specifically interesting for such approaches. And it was in many research studies that the optimization capabilities of living systems became evident, such as when, for instance, this slime mold following certain nutrients which were placed on a small-scale Tokyo map where the important cities are, basically reproduced immediately the logistically efficient Tokyo railway system, which originally was the product of years of engineering and optimization, but this organism just replicated it just because of its innate optimization capabilities. The structural organization of biological tissues, like bones and branches, also became a fascinating source of inspiration for engineers, as the computational tools to describe these structures became more affordable and more advanced. This is how biomimetics established itself as a design approach, the earliest example of which is probably the Eiffel Tower, where some inspiration was drawn from the structure of bones, the internal structure of bones. And certain engineering algorithms like topology optimization would become inspired also by the structure of bones and trees, and they would basically function in a way that they would optimize the volume of an object under specific stress conditions, just like an organic system, like a tree or a bone or a sponge would do. It was soon enough that designers also started relying on such optimization algorithms with which they could sort of explore organic shape and sort of justify it functionally with its structural intelligence. As robotic fabrication methods became more and more available, this pursuit of biologically inspired material systems opened a new page in design research, as can be demonstrated by the ICD and ITKE's series of research pavilions at the University of Stuttgart. This their approach focused on collaborating with biologists and using some advanced technologies like 3D scanning, algorithmic modeling, and CNC manufacture to very coherently translate the biological role model into a material system. And even though in most cases the biomimetics approach is to be understood as a form of an abstraction, not using the actual biological systems, but rather trying to extract a certain structural principle as an inspiration for the engineering of a product, such as, for instance, these bistable folding lamellas inspired by the carnivorous water wheel plant. Sometimes the products, the works went as far as to use some thoroughly engineered biocomposite with very similar properties to the original biological role model, such as these systems of hygroscopic platelets that open and close according to the air humidity, as inspired by the movements of the pine cone, which opens and closes during climatic changes. Now, if we zoom out of this sort of ivory tower of design academia, we have to see in what context this research is happening. As many of us know, the world is gradually entering the so-called fourth industrial revolution, an age of global interconnectedness, artificial intelligence, mass customization. But let's take a closer look at how exactly this expresses itself. Fabrication processes, along with many other processes in our everyday lives, are becoming increasingly automated. And robotics is not anymore just a subject of sci-fi, but globally there are substantial amounts of research into various forms of autonomous and semi-autonomous robots. For instance, drones, rescue robots, soft robots, nanorobots. And this, combined with the advances in artificial intelligence and computer vision, has even more sort of signifies an even more significant strive of humans to produce, to create some sort of semi-autonomous artificial life, which can assist us in more advanced tasks. This combined, this also projects itself on many sectors, not only autonomous vehicles, but also the construction industry, where there's research in many modes of robotic fabrication, production, and using different sorts of setup. Of course, still very much in the research phase, but we are seeing more and more examples happening in real life projects. This combined with the advances in additive manufacturing or 3D printing enables us to create more and more complex forms with differentiated structures, just like natural structures, on many different scales and with a wide range of different materials, such as steel, plastic, clay, ceramics, concrete, etc. At the same time, this interconnectedness and of the internet and the availability of information through it democratize the technology so that many people have the access to download and create their designs and fabricate their designs from the comfort of their own homes, which on the other hand triggers the formation of new modes of creative social interaction and collaboration, which we can see in the formation of fab labs or maker spaces all around the world. At the same time, on the digital side, we have the increasing advances in in augmented reality and in virtual reality, which enable more immersive design and fabrication interfaces, which further increases the possibilities with what we can achieve with all these tools. Talking about all these technological advances and computational capabilities, the same technology also allows us to observe and model and understand nature, including the biological environment, better than ever before. From the folding of proteins for the development of vaccines, through genetic engineering to 3D printing of substitute organs or prosthetics, we can observe that computation uniting science and design for very, very noble purposes connected to biological sciences. However, these very same insights and analytical tools allow us to also see the ever increasing environmental impact due to our technological progress. By now, it's probably not a secret to anyone that our rapid and ever increasing industrial growth and mass reliance on fossil fuels is causing a spike in carbon dioxide emissions. If we see it the last hundreds of millennia, this is an unprecedented event happening, which, as we know, has the effect of rising global mean temperatures, which causes the melting of ice caps and glaciers, triggering natural catastrophes such as glaciers sliding over entire villages, like this recent example in India that happened a few weeks ago, or the acidification of oceans, which causes coral bleaching. Another effect, that we clearly know is the forest fires, which happen with increasing frequency, releasing even more carbon dioxide in the air and cutting off the lungs that purify our atmosphere, and thus pushing the whole ecological imbalance further into a sort of a cursed loop. Another effect that is becoming increasingly irreversible is, and it's also linked directly to fossil fuels, is plastic pollution. It's disrupting the habitats of numerous ocean and land animals, and it's becoming the most visible mark of the Anthropocene everywhere around the globe. Even though there are a lot of efforts in research and design to counter this through the development of plastic-eating bacteria, or pushing recycling strategies, it's still a fact that the majority of plastic ends up in the environment. And as of 2017, this was basically 91% of it. Only a small percentage got actually recycled, which has to make us think about how we're facing this problem. There is, of course, a collective responsibility that we all carry, but architects and designers have an important share in this, because they are sort of complicit with certain industries that contribute to all these problems, whether it's through their choice of materials or the design approaches they pursue. We are sort of working with and for the mechanisms that are shaping the future of the planet. Whether it's the construction sector, which carries a lot of so-called embodied emissions through the production of concrete and steel, or it's fast fashion, or the consumer electronics that basically encourage a short-lived and reckless, short-lived products, which triggers more and more reckless consumerism instead of a repair ethics. So it increases the problems further. So, speaking as a member of the computational design community, I want to pose the question: how can we take all these amazing potential of the technology we have and the computational tools we have, combined with our advanced understanding of nature reflected through this technology, in order to reverse this negative impact on our environment to create a better future for humanity? To find this answer, first I want to look at the predominant relationships between design and nature throughout history. In its very origins, human technology started as a means to protect ourselves from the hostile elements of nature and to harness the useful ones. Therefore, technology helped us gain more control over our environment and therefore over our own survival. On the other hand, nature always remained an aesthetic role model as human art was developing. Some philosophers like Plato even described the origins of art as an imitation of nature. And the concept of the primal hut, which was stated by Marc-Antoine Laugier during the Age of Enlightenment, also described the prototype of all buildings as constructed from the trunks and branches of trees, which were basically the original building elements in the very beginning. The artistic merits of artworks throughout history resulted not just from the direct copying of nature, but also from its artificial ordering into symmetries. The more order and symmetries was brought to nature, the more artful and the more the superiority of the human reason would be demonstrated over the chaoticness of the chaotic character of nature. This can be clearly witnessed when we look at Baroque gardens, for instance. A little bit later on, with the evolution of the microscope as a scientific instrument, it was Ernst Haeckel who took a closer look at the fine-grained detail of nature's beauty and drew attention to the already existing order and symmetries in the magnificent world of biological life. the structures that constitutes all biological organisms. His work and his way of depicting these became an inspiration for the age of Art Nouveau, which was partly building up on the technology that was available, that became available throughout the Industrial Revolution, and demonstrated in a very artful way the state-of-the-art technology, which, with, for instance, with its fine filigrane plant-like curved iron ornaments. In its efforts to bring fine arts aesthetics into nature, it used exactly the ultimate role model for art, namely the forms of nature. Now, we skip to today's age, to the age of computational design, and one cannot help but notice the similarity in what is happening here. However, considering our current advances in our understanding of nature and our ability to identify ourselves within our world's ecosystem, this similarity doesn't look that much like a revival of a glorious epoch, but more, to me personally, more like a reversal to an anachronism. Because computational design is increasingly becoming more of a just formal manifestation that is chasing the realization of someone's digital dreams, following the philosophy that everything is possible at no matter what cost. And thus it is massively distancing itself from materiality and ecology instead of embracing these with the enormous capacity it has. So in some way it is failing to fulfill the designer's responsibility for creating a better future. The more this design methodology is becoming adopted by different industries and markets, it's falling under the very same pressure of the established planning mechanisms, stakeholders and clients, and it's becoming more of a commercial hype, a pretty story, but however, kind of devoid of deeper meaning, in a way triggering new forms of consumerism. While it does create very exciting narratives about customization, about optimization and adaptability of materials to certain aims, it seems to miss some of the bigger problems that lay ahead. And there is no doubt that computational design can produce stunningly beautiful artifacts as a form of art and envision some futures in a captivating way through their form language. But if computational design is to move beyond the purely aesthetic realm and establish itself in the industry more ideologically as a movement of the next human age, it needs to address some of the responsibilities that all designers face. And what I mean is kind of indicated in this example that I'm showing. Basically, this is a design inspired by the natural form of tree branches, but it's not utilizing their structural intelligence as a system like Fry Otto would do, nor is it using a material with similar properties as wood, but it's purely translating the looks into a design, which looks kind of foreign in its to the origins of it, and it's made with a much more costly material with a lot of embodied carbon and very expensive construction process, and in a way it can be seen as a kind of a post-material trend, but something like this, if we were to observe it through the very strict and moralistic lens of early modernist designers, what we're seeing is not only an environmental crisis, but also a crisis of material honesty. Of course, thankfully, there are a lot of positive contemporary trends that we can focus and look to, and this is something that I'm very excited to point the focus on. The ones, the trends that I find most interesting and relevant for the aforementioned issues are the ones, to me, that focus back on exploring biological systems, but not as a metaphor or an abstraction, but directly with the aim to create fruitful synergies with the actual unpredictable living and decaying systems. A key term that should be mentioned here is non-anthropocentric design. As this name suggests, this design approach revolves not solely around the well-being of humans, but also equally of the living organisms from our environment, through understanding the symbiotic benefits that this brings. Examples of this exist since the ancient times, as can be seen in the pigeon towers of Egypt and Iran. These architecturally dazzling buildings, which were made to host pigeons in them. And the droppings of pigeons were then used for fertilization, leather tanning, and production of gunpowder. Now, you might argue, okay, how is this different from a chicken coop, from like the little houses where you put chicken to lay eggs? Clearly, this architecture and the way it is devised, it demonstrates that these are spaces that can also be equally used and enjoyed by humans. There's creating more of a horizontal hierarchy between the species. One contemporary example of non-anthropocentric designs are these worm hotels in Amsterdam, which are spread out in different public spaces around the city, and they become an important social element because they encourage communal participation. How they do it, basically, these worm hotels are sort of like worm farms where people from the neighborhoods can go and dispose of their organic waste, the rests of their food, fruits and vegetables, so that they can be processed by the worms into fertilizer that can be used for the communal gardens. And while this may seem like a kind of a low tech, more like a almost grassroots solution, there are also multiple high technological startups and institutions addressing even more severe problems of our environment, like the death of our coral reefs. Using advanced 3D printing technologies, they are using the full potential of computational design to create complex structures with undulating cavities and spaces that can serve as foundation for the growth of new corals, sort of like basically an anchor from which they can grow, which gives them a head start in repopulating their biotopes. And while the depths of the oceans may seem quite remote to us, green plants in our cities and into our architecture is an idea that has been long recognized for its positive climatic effects on cities, especially during the summer. And while we all know that green facade systems exist, some of us are also aware that the cost of their construction and maintenance is quite high. And that is partly due to the fact that basically you're trying to host a living system on a structure that is designed to be as sterile as possible. However, there's this new research into concrete, into a special type of concrete that is specifically suited and designed to invite and host moss because of its porous structure and other properties, which has a potential to make green facade systems even more efficient. From working with living organisms to harvesting structural material from them, Neri Oxman and the mediated matter group have created some really visually stunning works, which I find truly illustrate what the biocomputational aesthetics of the future could look like, either by exhibiting the delicate process of silkworms reinforcing this base mesh of silk threads covering a hull with intricate patterns, emergent patterns of their behavior, or by using CNC fabrication to print with biologically based decomposable compostable materials such as cellulose or chitosan made from the shells of beetles and plant matter to create a biomorphic structure, which I find has perfect harmony between its form and material. So this proves that computational aesthetics does not necessarily have to detach itself from materiality, but can actually be true to it. So you can have an organic design realized in organic materials. Speaking of organic materials, there's a very positive trend of a revival of regenerative materials such as wood and bamboo, which have been very regular choice for computationally designed buildings as well, due to the affordability and of the material and its easy processability. And as long as this is combined with responsible sourcing, this can provide a viable alternative structural material, especially considering the new advances in construction methods such as cross-laminated timber. And it basically, what we are dealing with is a wonderful building material which captures carbon with the growth throughout the growth of the tree, instead of releasing it with its production. Our technology nowadays allows us to take things even one step further towards sourcing wood locally in the closest forest through advanced scanning techniques, and finding bespoke pieces that fit exactly the load-bearing criteria of a specific structural detail. After all, in their raw form, trees have very uniquely optimized configurations of their trunks and their branches. And if we match these unique configurations with the exact load-bearing requirements that we need in our model, then basically with these advanced sourcing and scanning materials, we can create something that has very low fabrication costs. And why not use these very same optimization intelligence of trees and embed them as a living structural elements in our designs? This is what Ferdinand Ludwig and the Baubotanic Research Group have been trying to achieve by inosculating trees, basically letting them grow together around artificial structural elements, thus creating a building with both a living structure and a living facade, which can very well regulate the building climate throughout the seasons, just like actual trees would do, except these are also the load-bearing elements. This idea of using living trees for construction is by far not new, because for many years, the Khasi people in India have been building and maintaining these living aerial root bridges in the jungle by successively weaving new roots to reinforce the structure year by year, and this knowledge is passed on generation by generation, and the technique with which they're doing that. Such types of living architectures question our established methods of planning. While normally we see buildings as the final static products of design, all of them in some way change throughout their lifespan, and they transform throughout the years, no matter if they're made of living or non-living materials. And as soon as you recognize that, you can ask yourself, doesn't this, can we not think about designing open-end processes instead of designing finalized objects? If we use more temporal modeling and prediction tools in our planning, it would make a whole new, it would open you a whole new paradigm of designing the future. This is, of course, quite a challenging task, even with our current technology, but already efforts are made to create some feedback loops between robotic sensors and living plants, so that machines can be informed by the plant's movements while simultaneously guiding the plant's growth to the extent possible. Of course, biological systems are not something that you can completely force out of its natural needs. But if we find this kind of biosynthetic synergies that work for both parties, we can have very exciting results. Of course, it seems like a far-reaching goal, but we already have the capabilities to grow biological materials that we can use as a replacement for toxic and oil-based products like styrofoam and plastic. Take, for instance, this rising wave of projects that use mycelium as a material. By growing it into controlled conditions, into a variety of shapes and sizes to fit different structural needs. Mycelium has quite good material properties. It has good mechanical stability and insulation capacities. And it also comes with a very peculiar aesthetics linked to it, which is, of course, something that you need to get used to, but it is something new and which has potential to be explored. Not to mention, of course, its beneficial biological, ecological footprint. And as a material, it can be further enhanced in its performance when coupled with an intelligent computational system and sophisticated fabrication techniques that allow more control over its shape and structure and basically improve its properties. Mycelium is only part of a larger ongoing trend of biofabrication that happens on many levels around the world. Thanks to the easy access to information, anyone can have the resources to grow some kind of biomaterials in their home, such as, for instance, the case of the kombucha leather, which is made of cellulose produced by the SCOBY bacteria that is usually found in kombucha tea and gives its probiotic effect. These and many more biofabrication processes have long been accessible to designers, even with a limited set of resources. And if you look back and compare this with the democratization of computational and digital fabrication tools like 3D printing, one cannot help but wonder if the next logical step would be to have biomaker spaces emerge as a new forefront of design research. And indeed, if you look, there are already a lot of communities forming around these topics. So some of the last mentioned examples blur this boundary between high tech and low tech, posing the question, is this something that is to be viewed as a reversal in the technological development of the human civilization or not? But the real question, in my opinion, is to whether we need to rethink the meaning and merits of high technology as it is. Now, high tech equates to the furthest advancement of human-made artifacts away from the supposed uncontrollability of nature. So in this sense, it's a conquest against nature. however, us humans, having already become the alpha predator of this world, we don't face that many dangers. We have fulfilled this conquest, and the dangers for us don't come so much from our subordinates to the natural elements, but rather from the lack of control over our own growth, which causes imbalance to the elements that goes back to us, because we're not adapted to these changes that are happening. Therefore, it is time to embed more ecosystem thinking as a central element of our technology, starting a new generation of high-tech, embracing biological systems back into our sets of tools, in some ways gaining even more control over nature, but thus gaining more control over ourselves. If we should argue if computational design has any room in this, we need to ask, is computation necessarily high-tech? As I may have illustrated, it is actually something as fundamental and nature-bound as the DNA translation algorithms that have existed long before us and are intrinsically defining all life. While the resources for human-made computation have so far been driven by high-tech industry, the insights that we have now, thanks to it, can be used to drive technology into a new age and to a new promising direction. And we can very much accept the current embrace the current political changes towards green policies and take them as an opportunity to redirect the efforts of computational design to the more challenging, in any case, yet more exciting goal of biosynthetic symbiosis. And this also means developing mindfulness and ecological awareness through increased collaboration with biosciences, harnessing the complexity of natural systems through the increasingly available computational instruments, nurturing not an invasive nature-dominating way of design thinking, but instead an approach of vulnerable ecosystem awareness, curiosity, and patience. Thank you very much. I hope I didn't overstep the time too much. I may have been even quicker than I suspected. So maybe we have time for some question and answers.
Okay. Thank you, Boyan.
So I have...
Thank you. So do you want to start with the question session?
Absolutely, yeah. I can see there's already some comments.
Okay. So if you want to start with Ernesto, do you think that computational design, instead of being a straight discipline, it dissolves the barrier between fields of knowledge?
This is a very interesting answer, and I also that's why I gave this disclaimer a little bit earlier during the presentation that initially I thought while I was still getting into this field, I was expecting it to be something just like the old schools of architecture, where they had their own program and their own sort of moral connected to it. However, I did naturally find out that in this sort of postmodern world we live in, it's not a straight discipline at all. It's more something that revolves around a certain methodology, and that it's more of an instrument that anyone can use for their own sake. However, because that instrument contains in itself so much potential in a way, and because it is intrinsically bound with all these different technological developments that I try to sort of describe with the context of our state-of-the-art technology, I feel like it probably what I'm trying to criticize here is what I'm sort of not criticize, but I'm trying to sort of imagine a kind of a path which sort of wraps it up into something that more people can be inspired by and can follow, like an ideal, because it shows a certain promising way forward. But I agree, it does dissolve the barriers between fields of knowledge, because computation is something universal, as I already stated.
Okay, next. Same, Ernesto. Studying that closely nurtures nature abilities and humanizing them, does this make us apart or more close to it?
That's interesting. In a way, that's probably the question. Are we, if we're appropriating, in a way, we have always been harnessing some elements of nature for our own needs. Does that mean we are humanizing them in a way, or what? Maybe what you mean is that we're sort of trying to steer natural organisms into working for our own interests. Which, does this make us apart or more close to it? I think it brings us closer to it in the sense that we are forced to understand these systems much better in order to work with them. And this, at least the way I'm imagining it, naturally, the more knowledge you gain about the system, the more ecological awareness you get, and you sort of start to feel how this system and your system coexist in mutual relationships with each other. Of course, I can definitely see how this can also be instrumentalized in some completely wrong ways, which cause more damage environmentally than good. But I'm talking about a scenario where it's more, we're trying to get along with the organisms, and yeah.
Okay. What do you think about the discrete design movement?
That it is a term I've come across. If I'm not mistaken, there was a computational designer, I forgot the name, who has been sort of promoting this. I have to admit, when I first sort of came across this definition, it was just like a brief introduction to it. I didn't entirely grasp the fundamental difference of discrete design. I think it was juxtaposed with organic design, or with like continuous design or something. I think it was more of like a difference in aesthetics, which both of which can be achieved by computational design, but in a way it was arguing. I couldn't quite get to the gist, to the bottom of this breakup between the two. But maybe you can enlighten me on that. I would be really happy to fill in my knowledge gaps, and I will definitely, like, after this lecture, read more about it.
Next, are we rationalizing intuitive knowledge we had, like these Indian people that build bridges with this?
That's interesting. So intuitive knowledge. The question is, did these Indian people, was their knowledge really intuitive, or did they also have a very sophisticated framework and even algorithms of building these bridges, because I'm quite sure that the knowledge that was passed on between the generation had very specific instructions of how these branches need to be tied. If you look, maybe I can try to go back to the slide. But you can definitely see that there are certain principles that they're trying to follow. Oh, I think I skipped it. So basically, there's a little pathway going in the middle of the bridge, paved with stones, and I think there's a hierarchy of the routes, which, for instance, the big ones serve as main members, and the small ones then become a filling until they grow bigger. So I would say this thing is almost as engineered as the Bio-Botanic example, this very German boxy representation of the same idea. But yeah, rationalizing, it's a good question. In some way, I know what you mean. It's probably the sort of this approach of our kind of like this Western idea of reason, and how it tries to be smart about everything, about things that were probably understood on different levels or in different modes, but we have our established scientific methods and etc. that we're following in our westernized technology, and I'm not saying we should stick to these at all. Like I think if we approach it, that's why I was questioning the nature of high tech in the end, because what is high tech after all? Like if you can create such fascinating things made out of living tree roots, like that is some, to me, that is some futuristic Avatar stuff. Like depends on the way you look at it, I guess. But yeah, good question.
Where to start the process of biomimetics design?
Where to start the process of biomimetics design? Usually, well, since most of my experience with biomimetics was from the Institute for Computational Design in Stuttgart. They always started with, because it was basically set in the framework of a student course, where you have you don't have a specific goal yet, but what we were doing is we started first with the exploration of different biological systems, and sometimes they even narrowed it down, say, look specifically at like sea creatures, or the shells of sea creatures, or look specifically at the shells of beetles. However, at the back of our mind, there was always some kind of material system that we had to work with. So basically, we knew that we have an industrial robot at the university which can mill, it can wind carbon fibers and glass fibers, it can pick up stuff from point A to point B, and then you start putting the pieces together. Okay, if I want to have a system made of wooden plates that the robot can mill with these joints, what is the closest example from nature that we can inspire ourselves from to know how to make an entire structure with just this detail of the joints. And then you come across some examples like the sea urchin shell, which surprisingly also has these little joints if you zoom in through the microscope, and they're basically very good against shearing forces. That's why they stay stable if someone steps on them. And but biomimetics is quite tricky. I admit it. It's especially outside of academia. Sometimes it helps if you have a lot of prerequisite biological knowledge. So when you come across some everyday problems, maybe all of a sudden something will pop in your mind, and you'll be like, oh, that thing in nature works this and that way. But I remember that as students, we were always very confronted with this notion in biomimetics, and in how strictly we should interpret it, and you know, where does the abstraction end, and when do you when is it completely different from the principle? But essentially, it's nothing more but an inspiration tool. So it's just like different designers have different methods to sort of generate their initial ideas and concepts. Biomimetics can be just another tool in the whole range of instruments that you can use to create your designs.
How do you feel you have impacted in the industry?
Me personally, well, that's I personally, like, I would normally have a very humble opinion of this. Like, I don't think well, maybe if I put it in a bigger context, like these collective that I've worked on, especially in Stuttgart, working with all these exciting minds, and getting in touch with people who then spread out all around the world doing their thing. We used to study together with George, actually, and many other cool people who started doing the same thing afterwards. So I think if you look at us as a sort of a collective of individuals, each one of us is sort of trying to make a little dent, a little push into the new ways of doing things. And what I can see now, I've already taught a couple of seminars on parametric modeling, etc. And I can see that with each year, there's more and more students getting interested in it and starting to do it, and then taking this knowledge to their design offices or to the which pushes the industry, etc. It's all like a domino effect. But an entire industry is quite hard to impact as a single person, obviously. but actually, this lecture, the way I gave it now, is something quite new that I wanted to share after some reflection in these last years, because in some ways I saw that how the industry was getting impacted from what person like me were doing, and then I was like, but is that the right way that the industry should be going? Maybe I've been too excited about this whole thing all along. Maybe I should look back and take a bit of a critical view and go back to the minds who are just starting to adopt computational design and be like, whoa, guys, like, take it easy a little bit. Like, yes, it's cool. However, think about certain responsibilities and not to turn it into this toxic field that we're gonna dump after a couple of decades because it's not useful anymore. So, but yeah, thanks for the question.
Well, I think those are all the questions. So I want to thank you, Boyan. It was a wonderful talk. And I want to thank you on the name of the university that it was great to have you here with us. And I think that that's all. Do you want to say something?
Well, I just, I guess I just want to say thank you once more. And yeah, it was very exciting for me to show all of this to you. I think, I hope it was interesting to you as well. Yeah, I'm looking forward to future developments in this whole field, and hopefully everybody will bring something back home from what they saw.
Thank you, Boyan. Thank you. It was amazing. It was an amazing presentation. I think I hope everyone enjoyed, and we hope to see many more this kind of presentation and at CEDIM.
Thank you, Georgie. Thanks a lot.
Okay. Well, thank you, everyone. Thank you, the participants, and this will be all. We close. Bye.